Hello and welcome back to Season 1, Episode 3 of our web series, Comprehensive and Intuitive Introduction to Deep Learning. This is part 2 of 2, where we are learning about different tuning techniques so that we can make our neural networks go much faster and learn more optimally. So, as a quick recap, in Episode 2 of Season 1, we looked at the input layer of the neural network and we looked at the output layer of the neural network. On the input layer, we learned about input normalization techniques, which allows us to take inputs on different dimensions, different scales, and then normalize that so that our training is more faster and it's more accurate. And on the output layer, I walked you through several different use cases from single output regression to multiple output regression to classification problems like binary classification, multi-class classification, multi-layer classification, ranking algorithms, and so on. And I showed you different output functions, whether it is linear output function or it is the softmax output function, sigmoid output function. I also showed you different loss functions that can be used and so on, right, for all these different use cases. So in this episode, in episode 3, we'll focus on the other part of the neural network, which is the middle one, which is the hidden layer. And what we'll study is essentially 4 or 5 different topics. The first one is that we'll talk about activation functions. I briefly touched upon that in the first episode, but we'll go into more details about activation function, what role they play in the neural network. We'll also talk about how do you initialize weights and biases, because that's a big part about how you train your neural network in an appropriate manner, in a fast way, and so on. We'll talk about how do you stabilize training so that you can essentially train across different varieties of different data and different variances among the data and so on. We'll talk about how do you speed up our training. And then we will talk about a problem called overfitting and how do you avoid that overfitting problem in neural networks. So let's jump right in. So let's start with activation functions. So again, just as a quick recap, we covered this in episode 1 as a quick recap. So if this is your neural network, as you can see, you have an input layer, we have an output layer, and then we have a single hidden layer here. You can obviously have many hidden layers, any number of input neurons per layer, and so on. And each of those neurons, as we explained in episode 1, is made up of weights, as many weights as there are in the prior layer. Here there are 2 weights per neuron because there are 2 inputs coming from the prior layer. There are 3 weights here per neuron because there are 3 neurons coming from the prior layer. And there's a single bias per neuron. And we basically said each neuron is divided into 3 parts. The first part is where your weights and biases are. The second part is what we call as a logit, which is a summation function. It does a summation of this input value multiplied by its weight plus the input value x2 multiplied with weight w2 plus b1. And then you pass this through what is called as an activation function. That's what we'll study today, right? So 2 aspects. One is how do you initialize these weights and bias values? And the second one is how do you pick the right activation function and what does an activation function actually do? And what's the intuition behind that? That's what we're going to study in this episode. Okay, let's get going. Let's start with activation functions first. Now, at a very high level, activation function serves 2 important purposes in a neural network. One is that they introduce nonlinearity, and the second is that they serve the purpose of what is called as thresholding. So, what are these 2 things? Okay, so let's start with nonlinearity. So if you look at real life, in real life, patterns rarely look like this. They are rarely a straight line where everything is growing linearly. And by the way, what is a linear pattern? A linear pattern is where you can draw a straight line between all the data points to fit that pattern. So the slope of this line is always going to be constant, right? That's a linear pattern. But very rarely do you see patterns like this in real life. Most of the real life patterns are more complicated. They would have curves and they would, sometimes it looks random, sometimes it looks more, there's an immediate pattern that you can identify, but for the most part it is a complex set of curves and turns and so on. That's what essentially makes up real life data. As an example, if you look at this, what would be a in a non-linear kind of pattern in real life? If you look at a graph like this, you cannot draw a straight line between all these data points. The data points essentially are connected through a curve that is not straight. You can essentially turn it around like this. If you go to another type of a real life use case, which is character recognition, for example, handwritten character recognition, it's a very common deep learning problem. And here I mean, how do you fit a straight line to any of these patterns, right? Or more commonly, if you're doing, let's say, full image recognition, let's say facial recognition and all that, there are so many features that can hardly be ever expressed through a straight line pattern. So that's why if you look at it, real life data is nonlinear. Okay. Now we have to bring that nonlinearity into the neural network. So again, as a very quick recap, a neuron in a neural network is made up of three parts. First is the weights and biases. That's the first part. The second part is what we call as a summation value or a logit. And the third part is what we call as an activation value. Again, quick recap of what is a summation or a logit. Summation or a logit is nothing but you take the inputs coming from the prior layer, multiply it with their corresponding weights in your neuron, add them up with the bias, and that becomes your summation value. Now, if you were to plot this, so if this is your z value here, and let's say this is your x2 and this is your x1. Now, if you were to plot this, regardless of what values you choose for w1, w2, and b1, or of course any value for x1 and x2, the plot will always look like this. It's going to be one plane. It's always going to be a straight line. And I'll show you that by actually plotting it in a few moments. So this is going to be always linear, right? So that's where, this is why it's called as a summation value, which is linear. Now, which means that if you were to do a two-dimensional plot, it will be a straight line. But let's say that in your real life, you already established that your data patterns are never just straight lines. There are a lot of curves, right? So how do you essentially take this straight line and fit this curved pattern? You can't. So you have to have a way in which you can turn that linear line into a non-linear line, which essentially means that you should be able to turn it, right? You should be able to bend it. So that's what the activation function does. So that's where the non-linearity part of an activation function comes in. What it does is that it tries to bend, when it's learning about this pattern, it'll try to bend those straight lines in a certain direction that fits this pattern. Obviously, one could ask, and by the way, how do you do that, right? The way you do that is you basically take the summation value, you pass it through some activation function. There are several different activation functions like ReLU, sigmoid, tanh, and so on. We'll study that today. But it's just a mathematical function that you just pass the summation value into, and it emits a non-linear value. And the non-linear value will, metaphorically speaking, it will bend or turn that line, the straight line. Obviously, the question you could ask is, how does it know that it has to turn the line like this? What if it turns the line this way? Or what if it turns the line that way? It could. That's all fine, because in a neural network, if you remember, initially your prediction is wrong, right? Your prediction of the pattern is wrong. Over time, through sufficient number of epochs, sufficient number of exposure through different types of variances in training and training data sets and so on, it will figure out in which direction it needs to turn. Right? That's where the whole gradient descent and the backpropagation algorithm comes in. But the key takeaway here is, because real life data has a lot of, curves and turns, which essentially which means that it's non-linear, you just cannot take the linear values and then learn from that. You have to turn those values into non-linear. So that's the first purpose of the non-linear function. And when you do this, what will happen is that this particular, what looks like a linear surface, will now become more turned. Okay, here. So let's do a very quick demo of that. Okay. So again, I've defined a collab notebook. I'm going to import a few modules here. These are some utility functions that I wrote to plot graphs in 2D and 3D. We're going to use that. We don't have to go through the logic of how these graphs are plotted. It's pretty straightforward. It uses matplotlib, so I can ignore that. Now let's go, and again, by the way, I've defined a few activation functions. I'll actually talk about this in more detail shortly, but let's skip the implementation for now. And let's go to this. So here what I've done is I've taken two weights, W1 and W2. I've initialized W1 to negative 0.7, W2 to positive 1.3, and a bias value of 2.0. Then I create some sample data for X1 and X2, right? The value is between 0 and 10 for X1, and I created about 100 samples. The value for X2 is between 0 and 20, and I created 100 samples. And if you remember, the formula for prediction is x1 times w1 plus x2 times w2 plus b1, correct? Now let's plot this equation. Let's see what happens. If you plot this equation, this for now. Let's look at this one. Okay. So what I've done is I've done a two-dimensional plot here between y and just x1 and y and then x2, and then I've done a three-dimensional plot between y on the vertical axis here and then x1 here and x2 here. Notice that it is a straight line, right? It's a straight line regardless of what values. Let's say I pass a different, completely different values of weight. Let's say I change it to let's say, I don't know, 2.9 positive, 2.9 minus, I don't know, 0 point, let's say, or 5. Weight is, let's say, 2.9 or something like that, and let's run it again. Again, it's a straight line. So regardless of what values for the weights you choose, the nature of this summation equation is that it is always going to be a straight line, right? I mean, if you were to take a more interactive plot, it will look like this. Scroll down a little bit. It'll look like this. See, no matter how I look at it, it's always going to be a straight line. Okay. Now I need to turn this. The way I turn that is to basically take the exact same values, right? And then I pass it through some activation function. If I do that, I should see that this thing would turn. Okay, let's go and verify that. So here I'm going to turn it using different activation functions, the same x1, x2, w1, w2s. Let's run that. So as you can see, this is the, okay, let's go. Let's see here. Okay. So this is again the same linear line. Yeah, no activation function. This is with sigmoid. Look at it. Right? It just turns. There's a curve that it takes. Correct? Again, we'll study what these are, what is sigmoid and all that shortly. This is a different activation function called tan h. It also turns. Then I have this thing called relu, which is a very popular activation function. Notice that what was linear there actually just has a turn here. So what we have established is that just by taking your linear logit or summation value and passing it through an activation function, you can convert linear numbers or linear data into nonlinear data. Now that is good enough for us to basically start to turn the line so that we can identify nonlinear patterns in our data. Right? So that's the first purpose of an activation function. Now let's look at another purpose of an activation function. It's called thresholding. So let's say the use case is to identify handwritten characters, okay, or numbers. So this one, I mean, as a human brain, you can identify very quickly that it is the number 2. Yeah. Now, how do I make the machine identify that it is a number 2? So one way to do that is I'm going to take this image and I'm going to basically divide this image into a grid of 10 by 10 pixels. Okay, so 10 pixels this way, 10 pixels that way. Now, what I can do is once I have an overlay of this handwritten letter or number on my grid paper, what I can say is that I can start to color this, right? What I mean by coloring this is wherever there is no presence of a pixel. Remember, there are 10 pixels wide and 10 pixels deep here. So wherever there is no presence of the character, those pixels, I'll basically make them black. Okay, so there is no, the number 2 does not appear in any of these regions of the graph, right, or the grid. So I'm going to turn all of them black. And wherever this appears, this number 2 character appears, depending on how much of it appears within each of these pixels, I'm going to give it a different gradation of gray or white. Okay, so for example, if a small portion of that appears in this pixel here, so I give it a gray color. Now a bigger portion appears here, so I give it more lighter white color. uh, Same here, more white color, here darker gray, and so on. Essentially you get the drift here. It's essentially what we're doing here is that we are trying to color each pixel based on whether that character appears within that pixel when it overlaid on the grid, and how much of it appears, and basically we determine the density or the choice of color, right, of each pixel based on that. So if you want to take math to this, what you're essentially doing is you're putting numbers on each of these pixels. 0 means black, 255 means white, because the number, if you take a grayscale value, it's between 0 and 255. 0 means black, 255 means white, right? And 20 means one color, gray color between that, which is more darker. 150 is a gray color, which is more lighter than 20, but less, more darker than 255 and so on. This is what I'm doing, right? Now let's take a three-dimensional view of this. Let's take this picture here and just rotate it so we get an isometric perspective of this. So it looks like this, correct? Now, corresponding to this, as an example, let's say each of these pixels is represented by one neuron in our neural network. That is just an example. It could be represented by, each pixel could be represented by multiple neurons, or one neuron could essentially represent multiple pixels. All that is possible. But as a sake of example, let's say that each neuron is represented by one neuron in our neural network, which means that you have as many neurons here, like in the 100 neurons, right? 10 this way, 10 that way. And each one of those neurons has their own summation value, correct? And when you take the input and then you start passing it through these values, it's going to be some positive or negative number, each of these things, correct? Now let's add a activation uh, function in between the logic and the final value. Okay. So what this activation function, let's say we are targeting this neuron here, okay, or this pixel here. So which means that this is a corresponding logic for that. And what this activation function should do is anything that is coming from here, any value, right? Because you cannot force it to be zero. And over training, it can start to get to zero if you want, but you can always not get it to zero, right? It could be some value. So one way to think about this particular use case, an activation function is, if in the training, if it can turn all these places where it should be zero to negative, then I could define an activation function that would essentially act as any value that is negative always emit a zero from here. Correct? If I can do it that way, then I can define an activation function, which by the way is called a ReLU, rectified linear unit, where if the logit is negative, regardless of what value of negative it is, right? Anything that is less than zero, correct? It is going to always emit a zero. So it is basically acting as a threshold here, right? It is activating this neuron or not based on the value of this logit. Like for example, if you take, let's take another neuron here, right? So let's say it is Z65. It goes through this activation function. Here, what it should do is it should emit a value of 255. Correct? Essentially, it is activating this entire neuron in its full strength. Okay. Let's take another value, Z93. It is basically activating it to a lesser intensity. So what the thresholding function of an activation function here is to basically figure out at what intensity or if at all each neuron is activated, right? Which is essentially the signal strength that it's passing from one layer or one neuron to another neuron. So again, very quickly, if you think about it, what we have done with an activation function is that we have introduced nonlinearity so that we can essentially model a neural network to identify patterns in real life which are not linear in nature, which are non-linear in nature. That's why nonlinearity is important. The second one is activation function also figure out how much of the signal strength it needs to pass through from one neuron to another neuron, which is from one layer to another layer, right? How much of the neuron needs to be activated, hence the name activation function. Okay, so that's what an activation function does. So what are the different types of activation functions? So let's look at that now. So again, we go back to our neuron, multiple weights, multiple inputs coming to that. As many weights as there are number of inputs, there are n inputs coming, so n weights, one bias, single bias per neuron. Yeah. So the summation value again is the sum of all these inputs times weight and sum them all up with the bias. Now, this we already established that this, no matter the value of x or y or b, this value, the fact that it is just summation, will always be a linear line. Yeah. Okay, now we pass it through an activation function. Let's study different types of activation functions. One very popular activation function is called the sigmoid activation function. Now we looked at sigmoid as an output function when I showed you in episode 2 the binary classification problem or the multi-label classification problem. Yeah. What a sigmoid does, as a quick recap again, is regardless of what value you pass to sigmoid, whether the value is a negative infinity or a positive infinity, negative 10, positive 10, negative 3, positive 5, it does not matter. Regardless of whatever input you pass, a sigmoid always squashes that input into a value between 0 and 1. The magnitude of the input can be anything. It will always output a value that is 0 and 1. So it's kind of doing a squashing kind of a function, yeah, between 0 and 1. And the mathematical formula to do that is pretty straightforward. So sigmoid will never emit a negative value, as you can see, and it will also never emit a value that is more than 1. And because it does not emit negative values, it's never going to emit a value that is less than 0 either. Okay, regardless of the value of the logit. Now, another type of a function is called as a hyperbolic tangent function. The hyperbolic tangent function also looks visually like a sigmoid function. But what it does is it also allows you to pass in negative, or it also emits negative values. What it does is while a sigmoid squashes any input value between 0 and 1, a tanh function, an activation function, squashes it between negative 1 and positive 1. Regardless of the input size coming in, it always squashes it between negative 1 and positive 1. And there you see your nonlinearity that's being introduced. A very popular activation function these days is called rectified linear unit. At a surface, it seems too simple, but through a lot of empirical observations, it has been observed to do really well for several different use cases. And what it does is that you can pass in any value to a ReLU function. If that value is positive, it will pass that value as is forward. If that value is negative, it will always pass a 0. So it basically mutes or suppresses any negative value and passes the positive values as is. Right? So that's what a rectified linear unit does. There are several different variants to ReLU. One of the variants is called leaky ReLU. So why do you need to have those variances? See, one problem with the ReLU function, while it performs really well in many use cases, is that it always suppresses negative values because it basically makes them 0, right? We saw that in the prior example in the thresholding thing where if the pixel, yes, as long as you can make the logit negative, it will always emit 0. But the problem with that is the moment you emit 0, that particular signal is completely shut off from your neural network. What if you want to essentially pass smaller values for if the input or the logit value is negative? That's where the leaky ReLU comes in. What leaky ReLU does is on the positive values, it'll pass the value as is through the system, just like ReLU does. If Z is positive, it passes it as is. But on the negative, what it does is that it kind of passes a very small suppressed value of the negative value, right? So it basically you take the value of Z, multiply it with an extremely small, something like a 0.001 or something like that, and pass that. So if you look at it, a small portion of the negative values are also passed through. So you don't essentially permanently, what you call as kill a neuron or an edge, right, in your neural network. That's the purpose of a leaky ReLU. Now, the implementation of all these activation functions can be actually be done in single line of code. It's very straightforward. I mean, if you look at sigmoid, and if you can express this function using numpy as this, tanh as this, it's very, very, very straightforward to do these things in Python, for that matter, any programming language. So some of the pros and cons of these activation function. For sigmoid, as we said, the pros is that if you have a problem where you want to squash a value between 0 and 1, in episode 2, we saw that in binary classification, multi-label classification, where you would like to emit something like a probability distribution. So the value is always going to be between 0 and 1. If you also want to do it through the hidden layers, then sigmoid is great because it does the 0 to 1. The problem with sigmoid is that it suffers from what is called as a vanishing gradient problem. We'll talk about that shortly today, but that's one negative. The tanh basically allows negative values also to go through because it squashes numbers between -1 and 0. So in those use cases where sigmoid is not sufficient, tanh actually does really well. In season two, I'll talk about recurrent neural networks or LSTMs, where tanh is used quite commonly. We'll study more of that in that season. ReLU is computationally very efficient because all it's doing is an if condition. If positive, pass it as is. If negative, always make it zero. It has this problem of what I call as dying ReLU, right? Where once essentially once a neuron is dead because activation value is zero, the likelihood of it being part of the entire neural network calculation is pretty much gone. And sometimes you don't want that, right? So that's the big negative of ReLU. However, given how through empirical studies, they have found out that ReLU works for several different use cases. So that has become kind of the default choice for most feed-forward neural networks these days. And leaky ReLU, as I said, has the benefit of passing some negative values so that you can minimize the dying ReLU problem. Okay. Again, let's just see this quickly in action. Okay, let's go back to this example that we had seen in season 1, episode 1. And what we are trying to demonstrate here is there actually a benefit with an activation function or not? Okay. And what I'll do is that I'll use this TensorFlow Playground application to use different types of activation functions, ReLU, tanh, sigmoid, and linear, and see how our neural network does in terms of training and identifying a pattern. The pattern that we see here is you have something like this, and you're trying to do a classification problem. And what you're trying to classify is that given some other dot, let's say a dot is, if I put identify dot here, should that dot be colored blue or should it be colored yellow, right? That's what you're trying to do. So focus on this graph here. Focus on this one here, which is the loss. As it's training, is the loss going down? Remember, the loss has to go down, which essentially means that it's identifying the pattern. And focus on the activation functions that I choose here. The rest of it, ignore it for now. Okay, we will study regularization and all that later in today's episode, but ignore all that for now. And by the way, our neural network has two inputs and one hidden layer with four neurons and one output and an output layer with two neurons. Okay, let's now run this with tanh as our activation function. Again, observe how quickly the neural network converges, which means that the loss drops down and it is able to identify something, a region here that separates the region outside it. Okay, let's run this. There you go. Within sub-seconds, milliseconds, right? It is able to basically draw a region and say anything within this region is blue, anything outside is yellow. And as you can see, the loss has basically gone down significantly and very rapidly it has gone down, right? Let's stop that and let's change it. Let's say I did not use any activation function, which is called linear. Let's see what happens now. The loss is staying at 0.508509. It's not converging. It's not able to draw this separating region to separate out these two different colors. I mean, I can sit here for a long time, will not be able to do it. Yeah. Okay, now let's say I change it to sigmoid. Now what happens? So sigmoid, it is learning, the loss has gone down. Let's see if it's going to continue to go down. It is going down, it's going down, it's going down. And boom, there you go. It took slightly longer than tanh, but it is able to draw these regions where it separates out the blue from the yellows. Let's pick, let's say, ReLU. See, same thing with the ReLU also, it's able to draw these regions, draw this region where you can identify blue from the yellow. So clearly, as you can see from our demonstration here, without an activation function, it's not able to identify this pattern. And clearly this pattern is not a linear pattern. It's a non-linear pattern because they're all, it's defined through all this curved region here. Correct. By the way, this applies to any type of different patterns too. Let's look at this pattern, for example. Let's say take sigmoid as our activation function. Let's run this. You see the loss has to go down. It's still at 0.502. But you can see in this picture here that it is converging. Right? It is converging. It's converging. And now it's able to separate out the blues from the yellows. Beautiful. If I change it to not using activation functions, that will be linear. Let's see what happens here. It'll just sit there. You'll not be able to converge. So, what we have established here is that activation functions help in identifying real life patterns because they bring in the benefit of introducing nonlinearity to the neural network, as well as it helps in acting as a thresholding function. And there are so many different types of activation functions. I just showed you 4 or 5 different activation functions, but there are so many different ones. And I mean, you can actually start off with ReLU as your default, but you can start experimenting with any different type of activation function that exists. And by the way, you can define your own activation function too. All you have to remember is that when you define your activation function, or for that matter, if you have an activation function, you also have to know how to compute its derivative. Because if you remember, the activation function is useful if you just go back here. So if you go back to our example here, I mean, an activation function is useful during the forward pass where you take your inputs and you compute the logic and then get the activation value for each of these things and then make a prediction. But in the reverse direction, as you're trying to make the neural network actually learn from the error or the loss, you're essentially doing using gradient descent algorithm to go and adjust all these weights. And the way you do the gradient descent algorithm is that you create a gradient. You can essentially figure out what change, and for example, this weight will result in the loss going down, right? And you do that, you ask this question of all the weights and bias values in all neurons, which means that you need to know for every activation function, what is the corresponding derivative function also. It's a very straightforward thing to do that. Basically, if you've done pre-calculus or if you've done calculus, you'll essentially be able to do this. But just remember that if you're coming up with your own activation function, you also need to know what the derivative corresponding derivative function for the activation function is so that you can apply that towards your backpropagation. I've covered this in episode 1, season 1, so you can go back and look at that again. Now let's look at the next topic, which is weights and bias initialization. Now, the choice of your initial weights, obviously the weights and bias get modified through gradient descent algorithm as you're training, but the choice of the initial weight is very important. Now, this is captured really well by this quote here. It basically says that training deep models is a sufficiently difficult task, that most algorithms are strongly affected by the choice of initialization. The initial point can determine whether the algorithm converges at all, with some initial point being so unstable that the algorithm encounters numerical difficulties and fails altogether. So, what this quote is basically saying is that if you, while it is true that you would want to randomly initialize weights and bias, if you don't apply some method to it, it's quite possible that your network will not converge. In fact, I'll demonstrate that through an example shortly. What the key takeaway here is that you have to initialize weights and biases correctly. Now, before we go into how do you do that, let's try to understand a very important problem that are inherent in deep neural network. Deep neural network means you have multiple layers and you have a lot of neurons per layer and so on. So one class of problems that you have is what is called as a vanishing gradient problem, and other is called as exploding gradient problem. So what is a vanishing gradient problem? So in neural network, if you remember, in the forward pass, you're making a prediction. Weights are not yet adjusted. If the prediction is off, using a loss function, you determine how off it is. And in the backward pass, you start to adjust the weights, but in a backward manner, which means that it starts with the back layer, the last layer first, fixes the weights and biases there, goes to the layer before that, fixes the weights and bias there, goes to the layer before that, and so on. So what's happening here is that the weight updates are happening in the backward pass. Now, let's say that the weight values are very small in the earlier layers. In this back propagation, as the weights are being diminished more and more, as it is coming to the front of your network, the weights become so small that they start to play a very insignificant role in that neuron, which essentially means that your neural network perhaps will never be able to learn because it has shrunk the importance of a particular neuron, which is appearing in the earlier parts of your neural network, in the earlier layers. So that's a big problem that needs to be addressed. And if you don't initialize weights correctly, you can end up with very small weights, resulting in a vanishing gradient problem. The reverse also can happen, which is the exploding gradient problem, where the weights are adjusted upwards and they are going on, keeping on going up and up and up, and you essentially start to have this problem called as an exploding gradient problem. Therefore, you have to create a weight initialization technique that balances out, and it avoids both these problems. Okay. Uh, so, as a general guideline, when you're initializing weights, the three guidelines that apply. Number one is that the weights must be small. You really don't want to take too small or too small or too large weight values, and they should be different from each neuron. Obviously, if you use the same weight initialization for all neurons, there's nothing that's being learned. Every neuron is emitting the same activation value, and when you're back propagating, everything will be adjusted back similarly. It really doesn't serve any purpose to have the same weight values for each neuron, and they should also have good variance. So there are two popular techniques through which you can initialize weights. The first technique is called Xavier initialization, also called as Glorot initialization, and the second one is called as a He initialization technique. And what both of them allow you to do is that you can, depending on the problem that you're trying to solve, you can initialize weights using either a normal distribution or a uniform distribution. A very quick recap: uniform distribution means if you're trying to generate a value between, let's say, 0 and n, the random values will be uniformly distributed between the 0 and n range. And in a normal distribution, they are more centered around the center here. So the more of the numbers that it generates are here, and there are fewer numbers that are away from the center. It's a typical bell curve normal distribution. So you have a choice of what distribution you want in your random numbers you generate. With this background, let's look at Xavier initialization. So what the Xavier initialization does is it basically looks at the topology of your neural network, and it introduces this concept called as a fan-in and a fan-out. A fan-in is how many neurons are connected to your neuron. So in this case, the fan-in is 2 because there are 2 neurons connecting to layer 1. So fan-in is 2. Fan-out is how many neurons that you connect to in the next layer. So in the next layer here, there are 5 neurons. 1, 2, 3, 4, 5. So the fan-out for this layer is 5. So we go to the layer after that, layer 2. Fan-in is how many neurons are connecting to your layer. There are 3 neurons connecting to the layer, so fan-in is 3. How many neurons are you connecting to in the next layer? 2 neurons in the next layer, so the fan-out is 2. Layer 3, how many neurons are connecting to you from the previous layer? 5. 1, 2, 3, 4, 5. So fan-in is 5. How many neurons are you connecting to in the next layer? 1. So fan-out is 1. So it basically uses this fan-in and fan-out, and basically has defined uh, some formulas here. So if you're doing uniform distribution, it basically says that I'm going to generate uniform numbers from a minimum of negative square root of 6 over the square root of fan in plus fan out, max of positive square root of 6 over fan in plus fan out. If you're doing normal distribution, then it'll generate with a mean of 0 and a standard deviation of square root of 2 over fan in plus fan out. Why the value of 2 in the numerator or square root of 6? You can study it offline. There is some mathematical demonstration of why these values are there. But again, through empirical observation, they found out that these values serve well. But the key observation here is that the denominators, right? It essentially is looking at the topology of your network, and it is picking numbers, random numbers based on the interconnectedness between the different layers. That's what Xavier does. Implementing Xavier is very straightforward. As you can see, the formulas for both Xavier normal and Xavier uniform are very straightforward. Implementing it in Python is just a few lines of code. In Keras, if you're using it, it is even more simpler. When you're defining a layer, all you do is that you say kernel underscore initializer equals, and you can use, let's say, glorot normal or glorot uniform, which is the same as Xavier normal and Xavier uniform. Okay, it's as simple as that. He initialization is another technique where they ignore the fan out. They only look at fan in. Again, how many neurons are connecting to you is the fan in. So fan in 2 equals 2 neurons connecting here. For layer 2, how many neurons are connecting in? 3 neurons are connecting in. Fan in is 3. For layer 3, 5 neurons are connecting in. So fan in is 5. They ignore fan out. The formulas are again defined here. If you're doing He normal, it is between negative square root of 6 divided by square root of fan in, max of positive square root of 6 divided by square root of fan in. And if you're doing He normal, it is with a mean of 0 and a standard deviation of square root of 2 over Fanon. Y square root of 6, Y Fanon. Again, you can study that offline. But again, key observation here is through empirical study, they found out that these values do well. Okay. Implementation again is very straightforward, just like in Xavier. If you're doing pure Python based implementation, look at the formulas. It's very straightforward to do that in Python, right? Using NumPy. If you're using Keras libraries, then again you import TensorFlow.keras.initializers, and then say for each layer you say kernel underscore initializer equals He normal or He uniform. Typically, you use the same initialization technique, whether it is He normal or He uniform or Xavier normal or Xavier uniform across all layers, right, of your neural network. So, when do you choose Xavier and when do you choose He? There are some general guidelines. It basically says that if your activation function is sigmoid, they recommend to use Xavier uniform. If your activation function is tanh, then they recommend use Xavier normal. And when to use He, if your activation function is ReLU, they say start with He normal. And if that doesn't work or it's suboptimal or it's taking too long to converge, then use He normal is what they say. Okay. Um, so let's actually see this in action. Let's see what would happen based on whether you choose Xavier or not. Okay. Okay. So there is this popular website deeplearning.ai, and they have put out a very good web-based demo to demonstrate the power of Xavier initialization. And the use case here is that they load the MNIST dataset, which comes by the way standard with Keras, and all it does is that it loads up some handwritten character images, and you're building a neural network that, given an image, will be able to emit the number that each of these images represents. For example, this image is going to say 7, this will say 2, and so on. Yeah. And you have different layers, different you know activation functions for these layers, and we need to just focus on this part here. And what you're looking for is how many of these input predictions are misclassified. Misclassified means it's supposed to be, let's say in this case, this one here, it's supposed to predict it as 7 and it is predicting it as, let's say, 3, right? It's a misclassification. And obviously you want this number to be as small as possible, right? Let's start with initializing all weights to 0. Even before I run this demo, you should know that if you initialize everything to 0, nothing should really happen. Your misprediction, misclassification should be very, very high, right? So let's run this. As you can see, your misclassifications are in the 90 range, right? So almost 90% misclassified. It's a pretty much useless neural network. There's nothing that you're learning when you're initializing all weights to 0. Okay. Now let's change that to, let's say, uniform distribution. Right? No Xavier, no He, just standard random numbers, uh, uniformly distributed. Here, I mean, it's doing slightly better than 0. It's gone down to 70. Sometimes it drops to 60% misclassified. Obviously, you want it to be much, much smaller. It's going to 50. What more iterations, it's going down a little bit, 40 and so on, right? So that's your uniform. Now, let's say I go to standard. Again, no Xavier yet. We'll come to Xavier shortly. And let's try to see how it's classifying. So here you can see again it's an 80-90 range, right? That's what's happening. Now let's just switch to Xavier and see what happens. Okay. So with Xavier, again it starts at 90, it goes to 60, 50, 40, 30, 20s, 40, 20s. So as you can see, just by keeping everything the same, the neural network architecture is the same, the activation functions are the same. All you're doing is you're changing the weight initialization to Xavier, and you can see that your neural network is able to classify these numbers more correctly, more accurately. So this is the benefit of initializing your weights correctly or choosing the right weight initialization technique. Okay, now that we have studied activation functions, we have studied weight initialization, let's look at bias initialization. So if you look at the formula here, there's something very interesting about bias. So this is where the bias is, right? In your summation value, you're adding the bias. So the interesting thing about bias here is that, weights actually multiply with the inputs that are coming from the prior layer, whereas bias are not, they're just added. If you go back to my episode 1, I show you that, weights allow you to turn the slope of your predicted curve or prediction, whereas a bias allows you to shift the location of your that line that you're predicting. Almost like if you go back to your algebra, right? Y equals mx plus c. M is your weight, which is your slope, and c is your y-intercept, as they call it, which is the how how much you have to shift your line on the y-axis, correct? So the observation here is that what the weights are doing is they are acting as something that amplifies the value, the signal value that is coming from the input. The bias actually does not do any of that stuff. It's just adding to this summation value so that you can shift. Okay, that's a very key thing. It does not essentially scale the input signal bias. It just shifts that signal because it's not really multiplied with any of the inputs. Therefore, it's kind of surprising. You essentially initialize bias to zero for the most part. It's fine. You cannot initialize, by the way, weights to zero. The moment you initialize weights to zero, you're essentially, because weights are multiplied with input, you're completely wiping out the signals that are coming from the prior layers. So you definitely cannot initialize it to zero. We already saw that with the demonstration earlier too. But bias, it's fine to initialize it to zero. And it could be completely wrong, but in the back propagation, it will adjust it up or down. So typically in a neural network, biases are always initialized to zero for all neurons in your network. Okay. And you rely on the back propagation algorithm to accurately move them up and down. For LSTMs, and which we'll study in season 2, uh, LSTMs stand for long short term memory. That's it, one type of a architecture of neural networks. There you initialize for something called as a forget gate, which we'll study in season 2. You initialize the bias value to 1.0. Otherwise, for every other neural network, the bias is always initialized to zero. So now we have studied activation functions in depth. We have studied how to initialize weights, how to initialize bias. Now let's look at another aspect of the hidden layer of your neural network, which is, how do you stabilize training across different layers? Okay, and we'll study a technique called batch normalization. So before we get into the details of batch normalization, let's try to understand what is the problem that we are trying to solve. The technical terminology for that problem is called internal covariate shift. Now, in 2015, there's a paper that was published that introduced a technique called batch normalization, which we'll study shortly, to solve for this. And that was a seminal paper because with this, you are essentially able to address some of the problems that exist in deep neural networks. What are those problems? For example, let us say that I'm trying to build a neural network that is trying to identify the pictures of roses. During training, I give it all red roses. And of course, I give it red roses, I give it non-rose kind of flowers of different colors, red and non-red and so on. Now the neural network has learned the nuances of how a rose looks and its petal structure and all that stuff, leaf structure and whatnot, right? Its size and whatnot. And it is able to learn, okay, this is how a rose is. But during inference, I give it a yellow rose. Now, everything else about the rose remains the same, only the color has changed. Yeah. How does the neural network now determine whether it's a rose or not? A similar problem, for example, is let's say that you're building a neural network to train on patient records at a hospital. During training, you basically train, it's an adult hospital. You train on all the patient pool there, and essentially the patient pool is between the age 18 and upwards. And you build a beautiful neural network that's doing accurate predictions and all that. Now, the same model, let's say, pediatric wing of the hospital wants to use, which is ages between infancy to 18 years old. But there's a shift, right? I mean, there's the distribution of the data has shifted from 18 and above to during training to during inference less than 18. So there's a problem, right? I mean, your neural network will not be able to do the correct identification or classification of the pattern. So that is a problem, and that is actually described technically using this word internal covariate shift. So what is that? There are three terms here, right? So let's try to understand this. A covariate in statistics is basically can be defined as such. So if you have, let's say, an input that is influencing an output, okay? Let's say that you're trying to measure the quantity of fertilizer you put, and you're measuring the health of your crop. So the quantity of your fertilizer is your input, and the health of your crop is your output, right? That's what you're measuring. But in addition to this quantity of fertilizer, there are other things that could also influence the health, which is not described in your input. For example, the amount of sunlight, amount of water that you're giving to your crop. That can also influence the health of your crop, right? So that is in statistics world, that is what is a covariate, where it is not really a direct input variable that you're giving that determines the output, but something that is indirectly influencing the output too, which is not described through your input variables. Now, obviously, we need to study what would that mean in the context of a neural network. I'll get to that shortly. But that is what your covariated is in statistics. But there are two other terms, internal and there's a shift. Now let's try to understand and map this to our neural networks. So I'll use this as my neural network architecture. Okay. So two neurons in my input layer, three neurons in my first hidden layer, four neurons in my second hidden layer, and one neuron in my output layer. And the data set I have is basically a sample set of age in years, the height in feet, and the uh, what I'm trying to predict is that what is the possible weight for a person with certain age and height. Okay. In our example, we'll only study, just for the sake of simplicity, only this neuron in this layer and this neuron in this layer. Same exact logic applies to every single neuron in every layer, but there's no point doing it for everything. We just study for just these two neurons. Okay. So what you do here is you have all these samples, right, which are there in your training data set. There are n samples in your training data set. For the sake of clarity, I've color coded them 1 through n. Okay. For a given combination of a comma b1, you produce some h1 here. Okay. Essentially, how is h1 produced? H1 is produced by applying an activation function on z1. And how is z1 produced? You take a1 multiplied with w1, add it with b1 multiplied with w2, and add the bias here, right? That's what you're doing. It's very simple. And by the way, it applies to everything like that. So let us say for each of the sample inputs, for the green input, I get some h1 value, let's say 10. For the blue input, I get a value, let's say 20. For the orange input, I get a value 15, and red and so on. I get different values. And now I want to draw a histogram. A histogram of what? Histogram of what is the distribution of these activation values that are coming out of this network. Which means that I basically say how many of these values, how many of these rows are emitting a value between 0 and 20? How many of these are emitting a value between 20 and 40, between 40 and 60, 60 and 80, and 80 and 100? All I'm doing is that it's basically nothing but a histogram of values that are coming out of this neuron, correct? And let's say that for the first epoch, the distribution is like this. A lot more of these H values are between, let's say 90, 80 and 100. Fewer than that are between 60 and 80. Fewer than that are between 40 and 60 and so on. Okay, this is the distribution. That's fine. Let's say we do this. And now we go on to the next layer. We do the same thing. We plot the histogram of values that are coming out for each sample H4 to this thing. And let's say the distribution is like this. Okay. No problem so far. Now your neural network makes a prediction. There's an error in the prediction. You determine that error through the loss function. You use backpropagation. You adjust all these weights and so on. Then you make your second pass through the second epoch of your training. In the second epoch, because the weights have gotten changed because of the loss function determining a certain loss. Let's say, again, I do the same histogram plotting. The entire distribution shifts this way. Okay, let's say it shifts this way. And for similarly for this neuron, it shifts in a completely different way. Okay, again, you predict an error. I say you make a prediction and you calculate the error, backpropagate, adjust all the weights and biases, run it through the third epoch. Now the distribution shifts like this. For this one, it shifts like that. By the way, the same thing can apply to each neuron, right? The distributions are different. See, as you can see, there is shifting happening in the internal layers. So this connects to the internal covariate shift. What is the covariate here? It's not just the inputs here. The activation values, right? They are also influencing the output. So your activation values are your covariates in your neural network. They are internal to the neural network between the input and the output layer. That's why internal covariate. It is shifting. The distribution of these activations is shifting across each training run, right? That's why it's called an internal covariate shift. This is not great because what's happening here is that in the first epoch, you're essentially made a prediction where, or you're essentially done the calculation where the distribution looks like this, and which might be wrong because it's not made the correct prediction. Hence, you're training it further. And in the next one, it actually shifts it all the way there. And then in the next epoch, it shifts it completely differently. So it's completely shifting so much. It's very hard. I mean, it takes a long time to actually train. So the shift is a big problem because your neural network is swinging from one distribution to the other, and there's no stability in the training between one run and the other. And this causes issues like if you're only having red roses during training and yellow roses during inference, you're not really stabilizing the distribution because for red, let's say it's all the values are in this side, and if you were to give a yellow during training, it would have been this side. You want to kind of figure out a way to kind of quote unquote normalize this distribution, yeah, something like this, so that as you're training across different runs, it follows some standard distribution of your data. So this internal covariate is your internal activation function. That shift is minimized. Yes, by the way, as I said, this applies to every neuron. The same logic applies to every neuron. Now, where have we seen this before? We have seen this in episode 2 of season 1, where I talked about input normalization. Remember, when the input is on different scales, for example, here I showed in episode 2 of season 1, you should go back and look at that. I did a full session on input normalization. What you do is that you center uh, your different features which are on different scales and all that to have a mean of 0. So you essentially center everything. And then you scale your data points across that center so that the standard deviation is 1. So now, even though your blue feature looks somewhere here, your green feature looks somewhere like this, and the yellow feature looks like that. When you apply your z-score standardization or normalization technique, look at that, right? All your input essentially start to look like a standard distribution like this. But the same logic we can apply it to the hidden layers too. So when you do input normalization, you're applying it to the input signals. Similarly, you can do what is called as batch normalization for the values that are coming out of this covariates, which are your activation values, correct? So you get all these H1 values for this neuron, H2 values for this neuron, H3 values for this neuron, and so on. You send it through this batch normalization function. And what this does is it basically emits some normalized values here. How does it do that? So as the name batch suggests, you're essentially batching your inputs because when you want to create a mean and a standard deviation, you cannot do it on one sample. You need to have a collection of samples. There's no mean to one single sample. There's a mean or an average to a collection of samples, right? So what you do is that you take all this data, input data, and then you divide it into mini batches. We already talked about that in season 1, episode 1. Let's say I create a batch size of 3, which means that I take 3 samples at a time and I determine that that's my batch size. So batch 1 is basically these 3 samples, batch 2 is these 3 samples, batch 3, these 3 samples, and so on. Once I have a batch of samples, I can essentially calculate their mean, correct? And then I can calculate the standard deviation. Then I can use the standard algorithm that we studied in episode 2, season 1. You should go back and refresh your memory if you have not seen that episode. The same technique that we apply for input normalization, we apply. It's a very straightforward calculation. So every of these input A and B values, or this H1 values, right, will essentially change so that they meet this distribution of mean being 0, which is it's centered around 0, and a standard deviation of 1. Right? So all these H becomes H1s becomes H1 primes, H2s becomes H2 primes, and so on. Same thing here. You apply the same logic here. Right? So this is your batch normalization. Now let's work through an example here. So let's say this is your input, okay? And you normalize H1 like this. So essentially for that batch, you take, let's say the distribution is like this, you center it around the mean of 0 and standard deviation of 1. For the green, you do the same thing. For the yellow, you do the same thing. Now, when we studied input normalization, we centered the distribution around a mean of 0 and with the standard deviation of 1. Now, is that the best we could do? Would it be better if we center it around some other mean and scale around some other standard deviation? For example, if you're centering around 0 with a standard deviation of 1, let's say it looks like this. But let's say that for the data, the centering could be around -5. So you essentially shift this distribution like this. And you also scale it from a standard deviation of 1 to, let's say, a standard deviation of 3. Okay, so you're scaling, you're shifting it from 0 to -5 here. This is centering. And then you scale it from a standard deviation of 1 to a standard deviation of 3. Would that make sense? Maybe it does. Of course, you don't know what is the right thing to center to. Maybe it is 0, maybe it is -5, maybe it's -3, maybe it's 10. Who knows what it is? And you don't know what to scale it to. But what if you can make your neural network learn that? That's very powerful. So what batch normalization does is that it actually modifies your batch, the standard, the normalization algorithm by first calculating your normalized values exactly around the mean of 0 and the standard deviation of 1. But then you multiply that with a value of gamma and a value, and then you add it with the value of beta. What the value of gamma does is that it basically works like it is scaling at a different standard deviation than 1. And what the value of beta does is it basically centers it or shifts it to a value that is not necessarily 0. But how do you know what is the right value of gamma and beta? We don't. It's great if you can actually make the neural network actually learn these two values based on the data that it is observing as you're passing it during training. So the way you do that is you essentially add, in addition to the weights and bias values, to each neuron, you add two more variables, two more parameters called the gamma parameter and beta parameter. And they are different ones for each neuron. Okay. And you initialize gamma to 1 and beta to 0 at the beginning of training. When you do that, when you initialize gamma to 1 and beta of 0, gamma to 1, which is essentially H1, beta to 0. So this one starts off with your standard distribution or normalization of meaning or centering around a mean of 0 and standard deviation of 1. And over time, you would like to figure out the changes, right? You start there. And now let the neural network learn. And just like you would adjust the weights and bias by creating a derivative of the loss over the weight, you would also do a derivative of the loss over the gamma and beta values. And over multiple training runs, the neural network will also learn what is the right value of alpha. Sorry, the neural network will also learn what is the right value of gamma and what is the right value of beta. Okay. Implementing it is very straightforward in Keras. You essentially import this module called batch normalization. And what you do here is when you are adding your layer, let's say you're adding the first layer, right? This which has 3 neurons. you essentially add another layer called the batch normalization layer. And after that, you add the activation layer. For the second one, you add the number of neurons, 4. Then you add a batch normalization layer. And then you add the activation layer. It's as simple as that. And this will take care of, you know, inserting the right logic within your neural network training, computing the correct alpha and beta values, and so on during backpropagation. But one thing to observe here, what I'm doing in this example is that I'm putting the normalization before the activation function is calculated, which means that I'm normalizing z values, not h values, right? Z values, not h values, which is fine. I mean, there are two schools of thought. Some say that actually you normalize the summation values, and some say that you normalize the activation values. If you were to normalize the activation values, then this line would essentially move under there. So you add the layer with the number of neurons, then you add the activation layer, and then you add the normalization layer. Both are fine. Again, as I said, there are two schools of thought. You can adopt one of those things. Now let's look at the other part of tuning your neural network, which is training. How do you speed up training? We already looked at activation functions, initializing weights and biases. We looked at how do you normalize the internal layer so that you avoid internal covariate shift. Now, how do you make your gradient descent algorithm go faster? So before we get into why do we need to optimize gradient descent algorithm, let's get an intuitive feel of what what would happen if you do not optimize. For that, I will take a very, very, very simple neural network to begin with. A single neuron, a perceptron, one perceptron, to which you're connecting one input, a single weight, and a single bias. And I will try to make a prediction. Now, let's say that the weights and bias values can be any value between, as an example, right, 0.0 and 2.0 with a precision of 0.1. What I mean by that is, the values of weight and bias can be any value between 0.0, 0.1, 0.2, 0.3, 1.0, and so on till 1.9, 2.0. Precision of 0.1, right? You're essentially taking 0.0 and adding zero point 0.1. So essentially, the value of weight and bias can only be this, let us say. Obviously, it can be anything, but just as a sake of example, let's try to understand. Okay, let's say it says between these values. Say 21 possible values, right? Between 0 and 20, including 0, it's 21 possible values. Now, A and B, if you look at the combination, they can be 0, 0.0, 0.0, 0.0, 0.1, or 1.0, 0.0, or 2.0, 2.2. So, how many such combinations exist just for one single perceptron? There's only one weight and bias. For 441 different combinations just for one weight and one bias value. Yeah. Which means that if you were to build a neural network that will lay out all these values, 441, and then figure out what is the right combination of weight and bias values so that, uh, your X is predicting the correct Y, which is the same as true. 441 different combinations exist. Now, let's just make a minor tweak to this neural network architecture. Let's add one more weight, just one more weight. Earlier, it was one weight and one bias. So now I have two weights and one bias. I pass the same input to these two things. You know how many combinations exist now? Just by adding just one more weight, 9,261 different combinations, which means that the neural network has to choose between 9,261 combinations. If I were to run this out and increase the number of weights from, let's say, two, this one to 10, I mean, just at, let's say, the fifth, let's say, four weights and one bias, there are already more than 4 million combinations. At, let us say, seven or six weights and one bias, it's more than a billion, right? And at about 10 weights, it crosses a trillion. This is with a precision of 0.1. Obviously, you will have bigger or smaller precision, right? Which is, let's say, precision of 0.01. Just with two weights. With 0.1, with two weights, it has 441 combinations. With two weights, it is, with the precision of 0.01, with just two weights, it is 40,000 combinations. You hit the 1 million at the fourth, third, three weights plus one bias. You hit a first billion at around, five, four weights and one bias and so on. So this is unworkable, right? You just cannot just go with the different combinations and weights and biases. These are like trivial size neural networks. You talk about large language models, you hear this thing that you have some 600 billion parameters and all that, right? So it's just not practically possible just by looking at all the combinations. That's where your gradient descent comes in. Because the gradient descent doesn't look at combinations, it basically uses the loss function, it calculates gradients, and it then starts off with some random weights and biases and it adjusts all that, right? But this slide gives you a good intuitive understanding of why the scale of the problem is so huge, right, in neural networks, that you have to have sophisticated and complicated algorithms so that your neural network can learn fast without going through all combinations. Okay. And by the way, I touched upon some of these optimization algorithms in episode one itself, where I talked about things like batch gradient descent was the initial thing where you feed the entire batch and you compute the gradient descent based on the entire batch. Then I said, oh, don't feed the entire batch of samples. You pass one sample at a time. We call that the stochastic gradient descent. I talked about why that is, it has its own limitations. And then we said, oh, maybe we can optimize it even further by creating mini batches. It's basically meeting the batch gradient descent and the stochastic gradient descent in between. It's called the mini batch gradient descent. You should go back to episode one, season one, to refresh your memory on this one because I walk you through examples of how this is done. We studied this. We also studied that, in the gradient descent algorithm, when you're updating the weight, if you take big steps when you're, each update for the weight, you take very big changes to the weight, then you would end up with this problem where you're jumping from one region of the loss weight curve to the other region. Go back to episode one. I've actually explained this in a lot of detail. So I said big steps is bad. We also demonstrated taking small steps is also bad because it just takes too long to get to the low loss value. So we talked about how do you fix this by starting big steps at the top when the gradient is high, and as the gradient is getting smaller, you take smaller steps to get to the bottom, right? And you do that by essentially multiplying the gradient with the learning rate. I've spent a lot of time talking about this in episode one, season one. If you don't remember this, go back and look at that. But the key takeaway here is that not getting gradient descent right, it results in an extremely long time for the neural network to converge, and sometimes it can never converge too. So obviously, there's a lot more work that can be done, on top of mini batch gradient descent to make it much faster, more optimal, and so on. But let's try to understand that in a little bit more detail here. Well, this curve we have already seen, and what he said is that when you're updating the weight, instead of just subtracting the gradient, we also multiply the gradient with the learning rate, which is a small number. But you know this curve, and again in episode one, I cover why this curve looks like this. In real life, when you have a lot more weights, a lot more doesn't have to be billions. It can actually be more than two, three weights, right? You would essentially see a curve that looks like this. It's not just a U type of a curve like this. It can have one or more such dips in it. Now, when you have a curve like this, and by the way, this is very realistic in real life when you have, let's say a cross entropy loss function with, let's say, three, four weights, right? You essentially see curves like this in three dimensions, or actually not in three dimensions, in n dimensions, n being the number of weights um, in your neural network. So there is this problem that, you have several local minimas and there is one global minima. There is one loss value, which is the lowest. But I mean, if you just look at the plot, there'll be several other loss values where the curve actually goes down, but then again it goes up and so on, right? And this loss value might seem, if you're just going down the hill, kind of climbing down analogy, it might seem that you've hit your lowest loss value, but the lowest loss value is at the global minima. So this is a problem that needs to be solved. I mean, if you took a three-dimensional representation of some curve like this is your local minima, and look at this, you have your global minima here. By the way, I got this beautiful animation from this website here. Um, but if you observe this here, right, you have your weights and your loss value. I mean, you can sit in here and thinking that you have hit your lowest loss value, but actually you're supposed to go there. So you cannot be at local minima, you need to get to the global minima. How do you do that? Um, we can use a technique that is there in physics called momentum to be able to solve this problem. Okay, and I'll tell you how we are going to use momentum to solve this problem. So without momentum, what we have done here is you start at the top point. Let's say your original, for whatever random initialization you weight, your loss was this. And using the standard gradient descent algorithm with the multiplication of the learning rate, you climb down and you basically get here, right? I mean, if you look at this picture, you go down and you hit here. But when you hit this low loss value, which is your local minimum, if you start continuing to go up, you'll see that your loss is increasing. So you would basically say, hey, no, 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 this is wrong. I already hit my lowest loss values. I'm going to stay here and I'm going to stop my training. But actually, your loss value here is the lowest, right? So how do you make it go past this? What if, again, the physics concept of momentum, as I'm coming down the hill, what if I catch enough speed or velocity so I can go past this and I figure out a way to get past this thing so that I hit this curve and then I go down, right? And think about it like you're cycling down a slope, and if you're cycling too slow, then when you get to the bottom of the slope, you can stop there. But if you are not applying your brake and you are essentially cycling as you're going down, you build up enough momentum that when you get to the bottom of the slope, you essentially go up again, and then you can continue. Correct? So how do you bring that concept into um, this gradient descent algorithm? What you do is that you change the formula. But let's actually look at this example here. You go down here. I mean, just let me do that again. It goes down and then it catches that momentum, then it goes here, and then it swings around this valley until it settles down at this value. Okay, so how do you get this concept in? So you essentially modify this formula by saying the weight. Earlier with this formula was what? The weight was, the new weight is the current weight minus the learning rate times the gradient. Correct? Now you modify it as that the modified weight is the current weight minus the velocity. Okay. Now the velocity is essentially defined as the prior velocity multiplied by some scaling factor, which is also a hyperparameter just like your learning rate, plus you add the gradient. So what this does is the following. I mean, the intuition behind this is kind of very straightforward. Let us say you're here and you're coming down this path. Okay. And let's say the initial velocity is 0. Okay. Now from there you come down to this point here. Now, when you're coming down to this point, what has happened is if you historically look at the plots here, you're going down in the same direction, yeah, and your gradient is dropping. From here, you go down here, you're essentially going down in the same direction, and your gradient is. So as you're going down the hill in the same direction, essentially the direction is the same, right? Essentially, what you're doing here is you're adding up the velocity. I mean, imagine if you're going from here to here, your velocity will get negated because there's a change in direction. But as you're going down and with multiple iterations, as you're going down and down and down and down, if you're going down in the same direction, then you essentially, you're compounding your velocity, and that's what you need to establish. So, I mean, the fact that the formula depends on the prior velocity, the new velocity depends on the prior velocity, shows that there is a history building up of velocities. The reason you multiply it with a factor here is you also want to discount the velocities that are, let's say you're here and you want to discount the velocity here. You want to give more prominence to the more recent velocities. If you don't do that, then what will happen is that the entire thing always gets added up, and you would get a thing where you would, you would essentially shoot from here to there and so on, right? You don't want that. So what you want is that while you're adding, you also start to discount, and the this fraction value here is usually 0.9 or 0.8 or something like that, which basically says that I'll only take 0.9, technically means I'll only value the last 9 values, and everything before that I'm going to discount. It acts like that. So just by adding this velocity thing, you would essentially be able to get past this thing and then keep going. Okay. Again, there's quite a bit of math behind how to tune this correctly and all that. And I think that requires a full episode on its own. So what I will do is that I'll create another episode on the formulas for the different gradient descent algorithms. But for today's episode, it is sufficient to understand that just by adding momentum, you are able to introduce a concept just like in the world of physics, where you can get past the initial dip and then go into the real valley where you can look get your global minima. So there's a beautiful tool that is built. I've shown you the link here. That actually gives you a very good demonstration of this. So here, this color, that ball, is the regular gradient descent, and the magenta ball is with momentum. Okay, and you can basically download this tool and build these animations yourself. And this is a local minima, this is a global minima. So both the balls start at the same place. If you look at it, right, the magenta ball can escape the local minima and get into the global minima, whereas the cyan ball cannot do that. Okay. And purely based on the fact that you're added this velocity component to the magenta ball, and when it comes here, it is going to catch up enough velocity so it can get past this hump, and then it'll go into, or get past this dip, and then it'll go into this larger global minima hole. Okay. Now there are several different algorithms like this. We talked about stochastic gradient descent in episode 1. We talked about mini batch gradient descent. Stochastic gradient descent with momentum is what I just showed you the formula for. Then there is another algorithm called Nesterov accelerated gradient, where they say, okay, in addition to velocity, I'm also going to dynamically adjust the learning rate. Remember that the learning rate was a hyperparameter that is fixed throughout the training run. But Nesterov or NAG basically also adjusts that. And one of the reasons for that actually is very illustrated in this picture itself. Look at this magenta ball. As it goes from the local minima to the global minima, it does not settle down there. It oscillates, right? It oscillates around that global minima because again, it would have caught momentum here too, so it has to go up. But that momentum should not be big enough that it will keep on going up. It will come down. When it comes down, again, it is catching some momentum, so it has to go up. But then again, it comes down. So basically, it's almost like, if you look at this picture here, if you look at this picture here, it comes down, it goes, the red ball goes down, it goes up, it goes down, it oscillates, and goes down. So obviously, you want to minimize this oscillation too. If you don't minimize oscillation, again, it will take a lot of time to, converge into the global minima. So there are, so many algorithms exist purely because people have figured out different techniques in which you can, by which you can tame how this approaching the global minima can happen. And all these algorithms, and there are several more, by the way, that are implemented. I will do a separate episode in talking about you know, how these models or how these techniques were built by the learnings from the prior techniques and so on. But we'll do a separate episode because that takes another hour or two on its own. But all you have to remember is that, over time, people have implemented different techniques. And right now, the go-to standard is what is called as an ADAM, algorithm optimizer, adaptive moment estimation. I've actually used this in episode 2 while I was walking you through the different use cases of binary classification and so on. But again, let's say see a quick demo of this. All these balls start at the same point, let us say at similar points. And the blue ball is with Adam. You see that it actually goes down very quickly to the global minima. The green ball is with another type of an optimizer called RMS prop. It takes more time to go there. Gray is Adagrad and so on. So the key takeaway here is that there's been a quite a bit of study and research in optimizing the gradient descent algorithm. And right now, as I said, the go-to standard is the Adam optimizer, which basically performs really well. Using that in Keras is very, very straightforward. You don't have to implement any of these functions yourself. All you do is that when you're doing a model.compile, you pass in the type of optimizer you want. And by the way, you import the different optimizers that Keras comes with. And Keras comes with a dozen or so optimizers, and you can pick from any of them. And as I mentioned, Adam happens to be a very popular and a very good optimizer. And right now it's the state of the art. So you can essentially start with Adam and it will do quite well for you. Okay. All right. Now let's look at the last part of our session today, which is how do you avoid overfitting? Now, first, before we get into the techniques of how to avoid it, we need to understand what is the problem that you're solving. Okay. Now, let's say the data looks like this. Okay. You have some data and you're trying to build a neural network that can identify a pattern like this. Now, let's say my neural network does learn a pattern like this. Is this a good learning? It's not, right? Obviously, this line is not is representative of this pattern. What would be the right pattern? It would look something like this, correct? Which means that it has basically identify that these are outliers and it does not fit your pattern to these outliers. That is your ideal optimal thing. But what if you keep on training your network and then it starts to learn every nuance in your pattern? Basically, it does a pattern that looks like this. So every data point is connected. Now, this is not good because what you're doing is that you're taking noise and also trying to fit a pattern through that noise. You don't want that. You essentially want to avoid that noise. Okay. The irrelevant details should be completely eliminated. So that is the problem that you're trying to solve. So if your neural network is learning all the irrelevant noise, that is called as overfitting. Okay. Now, the question is that why would that happen? That can happen for several reasons. Number one is that you have built a neural network that has so many layers, so many neurons, that it is trying to slice and dice every small sub feature of your, of your data set. And your data set is very small. That, it's overlearning. You don't want that. The other thing is that your training data set is so small that the neural network is so powerful that it is trying to memorize everything rather than trying to establish a pattern between in the training data, right? Or a third reason that would happen is that you have a lot of spurious noise in your data set, irrelevant noise. That could be the other reason why your neural network is going to overfit, and you want to avoid all these things. Correct? How do you do that? There are a series of techniques called regularization techniques that one can use to avoid overfitting. In this episode, we'll talk about three different techniques like that. One is called L1 regularization, also called as Lasso regularization, L2 regularization, also called as Ridge regularization, and then there's a dropout regularization. What are the key points here? What is the key insight on which this regularization is based? The key insight here is there are some weights that are more important than the others. However, the noise in training data results in less important weights also to influence the model. So from this key insight, what does it tell you? You want to suppress those weights that are not that important to fit the pattern in your data. Right? That is a key insight. These are all different techniques, but what are these techniques trying to achieve? They are trying to achieve by suppressing the influence of those features or those weights that have little to do with the pattern in your data. Okay. So let's start to understand each of these three different techniques now. What is the L1 regularization technique? The Lasso regularization technique is, again, you have a neural network like this, right? You essentially pass H1, H2, and all that is calculated as an activation function on top of these logits and so on, right? Now, what the L1 does is that it basically says, I'm going to suppress some of these weights completely and make them zero. Zero. Okay. Now, which means that these weights essentially completely are eliminated. When you eliminate these weights, what happens? These edges that connect these things, right? This, for example, just back here. This edge, this input signal will have no bearing on the value that is emitted by this neuron. This input signal will have no bearing on the value that's emitted by this neuron. In this case, this input signal, H2 and H3 has no bearing because you're essentially making them zero and so on, correct? You essentially take that out completely. So what is the core idea behind Lasso regularization? The core idea is that features that are not important, that describe the data that is, you completely eliminate them by setting their weight to zero, which essentially means that the remaining features are the more important one. That's why when you learn about Lasso or L1 regularization, they say L1 is a feature selection technique too, because you're selecting those features that are important and you're suppressing, completely eliminating those features that are not. Now, when you say features, of course, these are input features, but these are all sub features of the input features. Remember that in neural networks, internal neurons are splitting apart and trying to establish, correlations between the inputs that it sees from the prior layers and so on, correct? So these are also features in a way. And what you're doing is that you're suppressing some sub features completely by setting their weight to zero. Okay. And how do you do that? The way you do that is, the loss function that you calculate, the loss value that you calculate from the loss function. Remember, the loss function is used to take y true and the y pred and then compute the loss. Mean squared error loss function, we studied that. Cross entropy loss function, we studied that, and so on. You take that value as is, but in addition to that, you add what is called as a penalty. And we'll study that shortly. But you essentially add a penalty. In the case of L1 regularization, the penalty is going to be some hyperparameter here called lambda, which is typically a value that is greater than 0, between 0.01 and so on. And you multiply that lambda with the sum of all the weights, in your entire network, sum of all the weights. Okay. You take the absolute value of the sum of all the weights. Absolute value, the reason you take is because you don't want negative values to cancel out positive values. You essentially take the absolute value of the weight, add them up, and multiply that with a hyperparameter called lambda, which is basically any positive number. Typically, it's 0.01 and so on. Now, a small intuition here, we'll go into more details shortly, but a small intuition here is the goal of your gradient descent is to minimize loss. When you're adding up all these absolute values of weights, what will it do? Your gradient descent, because the gradient descent is going to be done not just on this loss, which is coming out of the loss function, but this loss added with this. It will try to make these weights also go down to zero. Because if the sum of all these weights are zero and you're taking absolutes, so negatives, positives don't cancel. So all positive numbers, if they're all coming down to zero, the smaller the number this is, the smaller the loss is, right? So that is the goal. While that is happening, the gradient descent algorithm is trying to adjust these weights. And we'll see shortly what will happen is that this, just by adding these absolute values, the unimportant weights go down to zero. How that will happen, we'll see shortly. What the key thing to understand here is L1, you add the absolute values of the weights multiplied with this lambda hyperparameter. What L2 does, and by the way, when you do that, with L1, you are essentially dropping certain weights completely to zero. What L2 or ridge regularization does is that it says, you know what, I'm not going to cancel out the weights completely. I'm just going to suppress them even further so that they play a much more diminished role in the final prediction. Okay, that's all L2 does. Instead of making the weights zero, which what L1 would do, what ridge or L2 regularization does is that it makes the less important weights even smaller so that their influence over the final model is going to be less. As you can see here, I've showed you through the graphics here, when these weights are made even more smaller, the signal strength goes down from the prior layers. In L1, the signal strength is completely taken out. Here, you actually suppress it. And you only do that for what? You only do that for those features that are less important. Okay. And the way the formula changes for L2 regularization is you essentially take the square of all the weights, every single weight in every neuron in every layer. You take all the weights, you square them, you add them up, and you multiply it with the same hyperparameter called lambda, which is again a positive value, typically 0.1 or so on. Okay. With L1, you saw it was basically adding up the absolute value of the weights. With L2, you add up the square of the weights and multiply, in both cases, multiplied with the lambda. Now, this brings up three important questions. The first one is, what are unimportant features which do not describe the data? The second one is, how does L1 move weights of unimportant features to zero? We need to understand that. When you're adding up all these absolute weights, how does it make it zero? Second one is, how does Ridge or L2 not move the weights to zero but actually makes them less? Closer to zero but never zero. We need to understand these three. Okay. Now let's explore the first question. What are unimportant features? So let's say we have a data set like this where we are trying to predict the price of a house, and the two input features are square feet of the house and the number of rooms it has. Now, the way in which you could express the price is square feet times weight W1 plus rooms times weight W2. For the sake of example, let's drop the bias. Now, if you inspect this data, what you notice is that the price is seems to be directly correlated to the square feet and very little or not at all with the number of rooms. For example, 900 times 2 is 1800 and 1000 times 2 is 2000, 1100 times 2 is 2200 and so on. So what this means is, the number of rooms has little significance in terms of predicting the price of the house accurately. So let's say that both these weights were initially initialized to 1.0. Okay. Now, as you're doing a training run, what would happen is that the weight of W1 would start to increase. It'll keep going up, and the weight of W2 will continue to go down. And the reason for that is the model is figuring out that pretty much two times the square feet of a house ends up being the price of the house. So over multiple training runs, you would see that W1 continues to increase or the weight increases, which means that the prominence of that feature increases, whereas the weight of feature 2 starts to go down, which means that the prominence of the feature 2 starts to go down. Now, as the training run progresses forward, you'll end up seeing, that let's say that the weight of W2 is completely zero, right? And let's say the weight of W1 is 2.0, you would essentially start to make the correct predictions, which means that the number of rooms or this feature is not an important feature in in order to predict the pattern in this data set. So the question here is, how does L1 make weights of unimportant features zero? You're adding up all the absolute weights here. How does it make it zero? Now let's look at this. You make a prediction. That's how you make a prediction. Y pred equals weight times x plus b. Correct? Now you calculate the loss. Let's say it's mean square error loss. You do this. Correct? Now what we already established is that when you're applying regularization technique, in addition to your loss, you also add, let's say your loss through your loss function is colored in blue. You add this additional regularization penalty, as they call it, which is lambda times the sum of all weights. Correct? So let's say the blue one is called L1, which comes from the loss function. The pink one is L2, which comes from the regularization value. Now, when you're doing a gradient upgrade, obviously you have to take a gradient of from both, right? The derivative of this, which essentially means what change in W will result in this gradient going down, or this loss going down, L1 loss going down, and this regularization loss also going down. Okay. I will not go into the details of, partial derivatives and all that. We can go back to episode 1. I covered this. Essentially, the new weight, if you apply this pink value, which is essentially the Lasso regularization, comes down to this. The new weight is, if the current weight is positive, the new weight is the current weight minus the learning rate times the derivative of this, which is this. Again, go back to episode 1. I'll tell you how this is a very straightforward calculus thing. Plus, this is the lambda. If the weight is negative, then it is minus the lambda. That's all it is. Exactly the same thing that you add either lambda or negative lambda. Now, the question here is that how does this end up making the weights of unimportant weights zero? Okay. So I'll give you a demo of that. But before I get there, let's also quickly also look at why L2 does not make the weight zero, but brings them to a very small value. Okay. So same formulation here. You take the loss value. Let's say it's a mean squared error loss function. This is what it is. You add a penalty term. In L1, you would basically add the absolute value of weight, all the weights. I'm just taking one weight here as an example, right? In L2, you essentially square it. So you have L1 blue, which comes from your loss function, L2 pink, which comes from your penalty regularization penalty function. So in the case of ridge regularization or L2 regularization, your new weight is going to be old weight or current weight minus the learning rate times the derivative, partial derivative, which again is covered in episode 1. You can go back and refer to that. Plus, what you're doing, the only change you're doing here is you're adding this penalty, which is 2 times the lambda weight, which is a hyperparameter, times the weight. Now the question is that why does this result in the weight getting diminished even further but never zero? And why does, in the case of L1 regularization, just adding lambda alone or subtracting lambda alone, depending on the weight, sign of the weight, make it zero? Now let's see a demonstration of that. So what I've done here is I've defined again some utility functions that is going to plot some graphs. I'm going to run a training run with 100 epochs. And I'm using a learning rate of 0.01 with a lambda value of 0.0, the gradient of 0.001. Now, what I've done is that because I want to calculate the values for, without regularization, which I call the original formula with just the learning rate, right? I mean, actually, let me write it down here. So if you look at the original, right, formula is what? Weight new equals weight current minus learning rate times the gradient, correct? And if you look at L1, which is Lasso, right, which is weight new equals weight current minus learning rate times gradient plus lambda if the weight is positive, or minus lambda if the weight is negative. Okay, let's just say plus lambda for now. And then L2, which is your ridge, is current minus learning rate times gradient plus lambda times weight current squared, right? This is what it is. So all these formulas are basically for W0 is, I'm representing this here as W0 variable captures that. W1 variable, sorry, WL variable captures Lasso, and WR captures ridge, which is L2. Okay. Uh, One more thing that is important to understand here is that as the weight is becoming very, 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 very small, there's a small optimization that is done, which is what is called as clipping at zero. So in order to not make the weights oscillate around zero, if it hits a very, very small value closer to zero, you actually make it zero. So for example, here I'm clipping it at a value of, very, very small value. Okay, 10 to the power minus 6 or something. Okay, now let's run this. Okay, so I'm starting what? I'm starting the weight at 0.002 for all original, Lasso, and ridge. Okay, 0.002 is my weight. Now let's just focus on this graph. Without regularization, I see that after 100 epochs, my loss my weight has gone down to 0.00190. It was 0.002, it has gone to 0.00190 after 100 epochs. If I apply lasso, what has happened is it goes down at the 20th epoch, it hits 0. For an unimportant feature, it has basically, this, let's say it's an unimportant feature, it has hit 0. By the way, if it were an important feature, its weight would have been higher to begin with. Remember that over multiple training runs, the weights are getting either bigger or smaller, right? Bigger when the feature is important. As a result, its weightage increases. Smaller means it's getting progressively smaller, means its weight is less significant uh, for the pattern that is there in your data. And what you're doing with regularization, if it's actually going down and down, you want to very quickly make it 0 with lasso so that it stays 0 and that feature is completely eliminated. With ridge, you want to make it not completely 0, but you still want to decrease it further. So here you can see same formula, right? I mean, same data point. It started 0.02. At the 20th epoch itself, you very quickly make it get to 0. And then, of course, once it gets to 0, because you're doing clipping at 0 here, right? You always keep it 0. With ridge, L2 regularization, again, it starts at 0.002. And at the 100th epoch, it is not 0. But notice that it is still smaller than without any regularization. If I were to put all the three graphs together, blue is L1 regularization lasso. It drops to 0 at the 20th epoch itself and stays there. So unimportant feature completely eliminated. In the case of red line, which is a ridge regularization, it is not hitting 0, but it is still less than what would be there without regularization. So the question is that why? Why is it going to 0 here? The reason is kind of very simple, because if you look at this formula here, you are adding this lambda value, correct? This lambda value is actually a very small value. So what you're doing here is that if the weight is not important, you're accelerating its descent down to 0 very quickly, which was not the case without adding this penalty here. You're accelerating its value. And you're accelerating it by what? You're accelerating it with this constant 0.01, 0.001, sorry, 0.01, right? You're accelerating that. And by clipping at 0, you ensure that it is not oscillating at 0, you hit it to 0. So, net, what you're doing is that you're forcing the weight to go down to 0 even faster. Why would this not have an effect if the weight were important? Because if the weight were important, this weight value actually is still pretty large, or is recently large. And its increment, because this lambda value is small, it will not suppress it down to 0 that much. Correct? And the question is that why doesn't the same effect happen with ridge regularization, L2? The reason actually is in this formula, because what you're doing is you're taking a small number, you're multiplying it with the weight, and you're getting a new weight. And the next run, the weight is even smaller. You're multiplying. So what would happen here is that this number is getting smaller and smaller. So let's say you take lambda starts at, right, 0.01. Okay. In the first run, let's say you multiply, and let's say your weight is 0. Let's say the weight is 1. In the first run, 1 times 0.01 times 1 is 0.01. Correct? In the second run, you take 0.01, you multiply it with this weight, right? 0, 0.01, which is 0.001. In the third run, 0.01 times this new updated weight, which is 0.001, is equals 0.0001. So what's happening is that because the weight is going down and you're multiplying it with a small number, it will never, I mean, what you're doing is that you're slowing down the decay or the thing, but it's almost like uh, it's almost like a binary back off kind of a thing where you're making it smaller and smaller and smaller each run. But because you're adding a smaller number, not a constant number, right? It will take a very, very, very long time, very many epochs to get to 0, which is what you're trying to avoid. But it's still better than not doing anything, because we are not doing anything. It still, that weight still has some significance. And again, remember, These things will only have some influence when the weights are small. And when are the weights small? The weights are small when you know that that particular feature is less relevant to fit the pattern that is demonstrated by your data. Okay. So these graphs clearly demonstrate that with L1, you can completely eliminate features that are unimportant. With L2, you can suppress their importance, uh, and so on. Okay. Okay. How are these implemented? Implementation is very simple. If you're using L1 regularization, using Keras, you basically import the regularizers module, and then you basically just pass to each um, layer. You basically pass the kernel regularizer equals L1, and this is the value, the lambda value that you pass. L2 is also similar. You import L2, and then you say kernel regularizer equals L2. It's a very straightforward thing, and this takes care of running the regularization, and you can do it on a layer by layer basis. The last topic we're going to cover is what is called as dropout regularization. So in L1 regularization, you basically eliminated weights that are unimportant. You made them zero. In L2 regularization, you basically made the unimportant weights smaller than what they would be without regularization. What if you can essentially drop out complete neurons altogether? Like, for example, let's say that you take this neuron out. So all this input is gone, right? So this neuron will not play any role in propagating the signal forward. In the next run, let's say you take out these neurons, right? In another run, you take out these neurons. In another run, you take out. So essentially, what's happening is that each run, a random set of neurons are dropped. So the key idea here with dropout regularization is you essentially remove the contribution of some neurons in making a prediction. Okay. So why is it done? It is done because you want to encourage the neural network to develop alternate paths to make predictions, which is actually very useful because when you have a very dense, complex network, you do definitely want the neural network to figure out different ways in able to basically stitch the patterns together through different neurons to make the prediction. By the way, these things don't have much value when your neural network is very small, but in practice, you have very large neural networks, so it actually makes a lot of sense to have the regularization techniques applied. So dropout essentially is, as you can see in this animation here, it randomly drops out certain neurons at each layer so that your neural network over multiple training runs finds out alternate pathways to basically make predictions. Okay. Implementation using Keras is also very straightforward. You essentially import the dropout module, and then you add a dropout regularizer. What it does is, so basically here, if you notice, right, I'm adding one layer, then I'm adding a dropout layer, uh, and then I'm adding another layer, and then I'm adding another dropout layer. What this does is, you say the first layer, you say dropout of 0.4, which means that with each training run, randomly it'll pick 40% of the neurons and it'll just basically drop them in that particular run. The next run, it'll pick another random set of 40 neurons in the same layer. In this next epoch, it'll pick another random 40 neurons and so on. And in this case, it'll drop the randomly pick 10 neurons in this layer in the first run, randomly pick another 10 neurons and so on. So its implementation is very simple. Also, you notice with Keras, you saw this as batch normalization also. Everything is modeled like a layer, although it's not really like a layer in the nomenclature used by the neural network world, where you have layer as basically a collection of neurons. But from it, when it comes to implementation, Keras models everything as a layer, so you can just add and stack uh, different features. So, for example, if I wanted batch normalization in between this, I can just say model.add batch normalization. So, boom, I can have that too, right? So that's the whole the implementation philosophy behind Keras. Anyway, so what we have learned is regularization is a technique which will allow us to avoid overfitting in large neural networks that we build out, with many layers and many neurons. L1 regularization is used when you have your data set which has many features, but intuitively you feel that there are some features that are less important than the others. For example, if you have a patient pool and you're trying to make a prediction based on whether the patient has a disease or not, perhaps in that particular disease, the height of the patient has less relevance, or the color of the patient has less relevance. You know that, I mean, I don't want to cleanse all the data because it might be hard to do that. So I can basically avoid that particular. I want the neural network to figure out that that is not going to have a significant role in determining whether the patient has that disease or not. So you would use L1 regularization. In L2 regularization, again, only matters when the neural network is very large. You do not know which feature is important, which is not. So you essentially apply L2 regularization, and over the neural network, while it's adjusting weights, if it feels that there are certain weights that are always remaining low, it will suppress them even more and more so that it does not end up in overfitting those data points or those features also into your pattern. With dropout regularization, you essentially want your neural network to identify alternate pathways to get to the prediction, typically used in recurrent neural networks, which we learn in season 2, or convolutional neural networks, which is used for image recognition and all that. That's where your dropout regularization is used. Now, another topic, the final topic that we'll cover, is what is called as residual connections. Now, what is the problem that residual connection solves? Again, let's say you have a very deep neural network. In a deep neural network, you have multiple layers, correct? And we established that there is this problem of vanishing gradients. By the way, the benefit of deep neural network is that your neural network can tear apart, slice and dice your data, and learn sub features, sub features, and all that. So you can make very good predictions. But the problem also with the deep neural networks is that you have this vanishing gradient problems, because the depth of the neural network is very large. If the weights are small, as the gradient propagation is happening in the backward pass, right? Gradient descent, the the values descend, they diminish so much that they'll essentially completely vanish away, right? So, which means that you need to somehow figure out a way in which you preserve signal strength uh, in a deep neural network. That's what residual connections or skip connections do. So there was a seminal paper written in 2015 where they introduced residual connections in image recognition, and they started to see that the neural network started to perform really well. And since then, it has become a common practice to use residual connections in deep neural networks. Large language models actually use it. If you look at transformer model, which I'll show you in season 3, it actually uses residual connections. The idea again is very, very simple. The idea is that you would like to create short circuits in your neural network. Typically, a neural network is a linear flow of neurons and the layers like this. In between, you'd also want to create short circuits so that the signal can propagate and jump. In addition to flowing through the neural network, it also goes to the some more neurons ahead in the layer pipeline. Um, Again, the idea is very simple, right? And the idea is basically that it will eliminate the vanishing gradients because the signal strength is getting amplified by passing the signal from prior layers to some layers into the future, right? Implementation is very simple. Let's say this is a neural network with 6 layers. As I say, as an example, I'm just taking one neuron per layer, which means that one weight. Input comes in, you calculate the logit as input times the weight of this layer, and then you take an activation function. This activation function goes to the second layer. That activation times the weight of this layer, you calculate the new logit, pass it through the activation function, it goes through and so on. So by the time it comes to Y prediction, it goes gone through all these layers and all these weight multiplication. With residual connections, you create different blocks, okay? Which means that let's say you create, this is one block, there's another block. So you take multiple layers and you create blocks out of that. So you take your X, you pass through, just like you pass here, right? You take X multiplied with the weight of layer 1 here, calculate the logit, pass that logit through activation function here, calculate the activation value, take that to this layer, multiplied with its weight there, and take H2. Now, what you do is that you want to also amplify this one with this signal here. So you skip, or rather, you connect a residual connection here. So what gets passed here has to be a combination of H2 and X. That's what you do. So you create a residual value, which is H2 plus X. Normally, you would just take H2 and pass it here. Here, you take H2 and also pass this X value and pass it here. The same thing applies now, right? Going forward, again, you take this R1 and you pass it here. So which means that what gets passed to layer 5 is H4 plus R1. Correct? And so on. So this is your residual connection concept. Okay? Useful only in very large networks. Large language models use it all the time. Convolutional neural networks for image recognition use it all the time because you need large networks to essentially slice and dice your data to identify patterns, both in text as well as in images. Implementation is very simple. Again, you create a residual block as I showed you. This is your residual block. And in the residual block, you figure out how many neurons are coming into the block. You save that. Then you create all these, you know, different layers in your block. And the output of one goes to the input of the other. It comes out of the output, it goes to the input of the other, it goes to the output, input. And then you take this residual and you add it here, right? This, whatever you saved here, you basically add it there. This is your block. Then you can essentially stack up all these blocks and you build out a neural network like this. So it's a very straightforward implementation. All you're doing is that you're just saving the input here, and then essentially you add this input to whatever is output here, and then so on. Okay, that's what your residual connections or skip connections do. Now we have come to the end of our season 1. So let me do a quick summary of what we have learned through the entire season, all 3 episodes of our season. So what we have learned is that you need to know what problem you are solving. Types of problems you're solving is the regression problems, which is you're predicting numerical numbers. Classification problems, of which there are 3 types of classification: binary classification, or multi-class classification, or multi-label classification. Ranking is another type of a problem you're trying to solve, or generation is another type of problem you solve. We covered these regression and different classifications and ranking in in season 1, episode 2. And what we have established is that once you know the problem you're solving, you will know how many output neurons are needed, which means that you'll be able to figure out the structure of your neural network. You'll know what output function to use, what loss functions to use, right? We have studied this. So as now that you know how to map the problem that you're trying to solve, or the use case you're trying to solve, to the architecture and the output function and loss function, step 1 is done. Step 2 is you need to apply appropriate tuning techniques. We talked about applying normalization techniques to the input. Why did we do that? Because features could be in different dimensions. For example, if you have an input feature like predicting, for the use case of predicting the price of a house, where the different features are square foot of the house, which is measured in, let's say, thousands, the number of bedrooms, which is measured between 1 and, let's say, 10 or so on, the price of the house, or the, you know, something else which could be measured in millions. So different, the ranges of values could be different for each feature. So you want to normalize that so everything follows a standard normal distribution, right? We studied that. We studied that on the output. We studied different types of output functions, when to use sigmoid, when to use softmax, when to use linear, when to use different types of loss functions. We studied all that. We also studied in the hidden layers different types of activation functions like ReLU, sigmoid, tanh, leaky ReLU, and so on. Throughout the network, what we also learned is we have to batch normalize to eliminate the internal covariate shift. Remember the problem that I said? During training, you're giving red roses. During inference, you're giving yellow roses. Batch normalization is a technique by which you can, just like with input normalization, you're normalizing the batch, then the activation function values within the internal layers, eliminating internal covariate shift. We also learned that weight initialization, like Xavier and He, are important. I gave you a demo of that. Then we learned about optimizers. Without optimizers, we said that you can get stuck within the local minima. Ideally, if you have multiple minimas and you have one global minima, you want to get there. We studied this technique of using momentum as a way to basically build up enough speed so they can get past the local minimas and get to your global minima. I showed you multiple, uh, you know, there are different options for doing optimizers like Adam, RMS prop, and NAG, and so on. And as I said, I'll do another episode later on where I'll go into the more nuances of these optimizers. But we did study how to use these things using Keras library. Then we said if you have a very large neural network, and you have data sets where certain things are not important. Regularization, whether it is L1 Lasso, L2 Ridge, or Dropout, are very good techniques by which you can eliminate overfitting problem that exists in neural networks. And then we studied residual connections for very large networks where you want to propagate signal strength further down your neural network chain, which, as I said, right, is very useful in both image recognition problems as well as in text recognition problems, which I will cover in season 3. So that completes our season 1. What I will cover in season 2 is going to be very interesting topics, which is working around text. How do you take text and build models around text? And I'll talk about different strategies in dealing with text. How do you encode text into numbers? How do you tokenize text? I'll talk about techniques called word embeddings. Then I'll also show you how to work with time series data. Then I'll introduce you to two new architectures of neural networks. One is called recurrent neural networks, which is very important for time series and text based data, and an optimization of recurrent neural networks or RNNs called long short term memory or LSTMs. So until next time, happy learning and subscribe to my YouTube channel, which is shown here. Thank you.